It is given that the heats of neutralization of a strong acid Ha and a weak acid Hb with sodium hydroxide are minus 13.7 and minus 12.7 kilocalories per equivalent. When one equivalent of sodium hydroxide is added to a mixture containing one equivalent of strong acid and strong base, the enthalpy change was found to be minus 13.5 kilocalories. Now we need to find out the ratio in which the base is distributed between the strong acid and weak base for the neutralization. Here, let the equivalent of strong acid be equal to X and the equivalent of weak acid be Y, and it is given that X plus Y value is equal to 1. We are adding a mixture containing one equivalent of strong acid and strong base. So XY is equal to 1. And whenever this entire one equivalent of this mixture is neutralized with sodium hydroxide, and that too with one equivalent of sodium hydroxide, the heat released is given as 13.5. Means X equivalent of strong acid, that should with heat of neutralization of 13.7, and Y equivalent of weak acid with heat of neutralization as 12.7. Whenever they neutralize, totally we are getting 13.5 kilocalories of heat, isn't it? For one equivalent we get 13.7 kilocalories for the case of strong acid and 12.7 for the case of weak acid. As we have X equivalent, so it is X into 13.7, Y equivalent Y into 12.7, and this total value is equal to 13.5 kilocalories. So if we take this one as equation 1, this one as equation 2, when we solve this, we get X value as equal to 0.8 and Y value as equal to 0.2. Therefore, X by Y is equal to 4 upon 1. The sodium hydroxide is distributed among the strong acid and weak acid in the ratio of 4:1. So our answer is 4.